This fixed problem is implementing an IRR filter algorithm in Vitis. Digital filters are often described and implemented in terms of the difference equation that defines how the output signal is related to the input signal. This formula represents a general form of an IRR filter, in which P is the forward filter order and Q is the feedback filter order. AIs and BIs are the filter coefficients. This code shows a software-oriented implementation of the algorithm. If we synthesize this code with Vitis HLS at 150 MHz for the Ultra 96 version 2 board, this figure shows the corresponding synthesis report. As can be seen, there are two violations in the report: timing violation and initiation interval violation. Whereas the timing violation may cause errors in the final results, the initiation interval violations reduces the performance. I have assumed n is around 1 million and p and q are 3. Then the execution time of this kernel would be 4028.2 milliseconds. And the computation results are not correct. Now the question is, how can we improve the performance and address the timing violation? Pause the video if you would like to give this problem a try, and when you are ready, keep watching to learn how to solve this problem. Note that you can find the Vitis code in the GitHub site mentioned under this video. The main reason for these violations is multiple accessing the vectors x, y, a, and b in the code, while these vectors are located in the main memory and the access patterns are not sequential. To solve this problem, we can define 4 buffers in the FPGA VRAM and modify the code. The idea is to have 2 shift registers to keep a window of input and output data required for the IRR computation inside the FPGA. This, firstly, helps to reduce the accessing data to the DDR memory, which is very expensive. And secondly, it makes the accessing to the DDR memory sequential. So, in the code, first we define the shift registers and then initialize them with data. Now we should write the IRR code. This loop reads the input value and shifts that to the X buffer. Then we use 2 unrolled loops to implement the IRR calculation. Note that here I have assumed that the filter orders are less than Pmax and Qmax. Finally, we should update the Y buffer and send out the output data. Now, if we synthesize this code and run that on the Ultra 96 version 2 Zinc MPS OC board, the report would be like this, which doesn't show any violation. And the execution time would be 1952.14 milliseconds, without any error in the output data. This code modification makes the IRR 2 times faster, but notice that the result data of the first implementation was not correct. If you have a look at the final synthesis report, still one loop is not pipelined. Can you think of a solution to pipeline this loop and improve the performance